Good. So many thanks for the invitation to give a talk today in this lunch lecture series. And I will talk a bit about ore deposits. I will talk about ore geology and geology, mineralogy, and how that can connect to mining of metals as a fact. But before we dive into the sort of the wonderful world of geology, I will spend just a minute to talk a little bit about myself, actually. Just giving you the background of sort of the reason why I'm sitting here talking to you today. So in this sense, I do not see myself at all, in fact, as a representative for the mining industry. Even if I'm doing ore geology, I'm a scientist and I'm a geologist. This is what I'm doing. And I have worked for a number of years now with looking at the trace element distribution in the bedrock, in the Earth's crust here. And trace elements would be elements, metals typically, that occur in very low concentrations. And I have worked now for 20 years looking at the gold in the crust here. And gold occurs as very, very small grains, and which means that they are difficult to find, which makes it more fun for me while I'm doing my research. So I've spent a lot of time finding rather small things, gold, but also other metals, which today is known as sort of critical metals for the European Union, like tungsten and cobalt and so on. But the past few years now, I have sort of turned or tweaked my research more away from gold a little bit and more towards carbon dioxide, and working with the geological storage of CO2 and the mineralogy and geochemistry related to that. So my foundation basically is that I worked a lot with mineralogy and various types of microanalytical techniques, and to use those tools to address different themes, such as understanding how an ore deposit was formed, or addressing the mine waste, looking at the mineralogy of the mine waste and the potential environmental concerns that might arise from that. I've also worked a little bit with metal recycling, which is surprisingly similar in the mindset, looking for gold particles in electronic scrap, same as looking for gold particles in the bedrock, basically. So very similar. And then carbon capture, CCS, and also mineralogy and characterization of meteorites. So sort of rather wide field of applications for this one. And I put in 3 pictures to the right here. The upper one is me. I typically work with rocks. I look at rocks. That's what I do. If I didn't do that, if I wasn't a geologist, I would probably be a nature photographer. And if I wasn't that, I would probably be a scientist. Science is sort of core for me. Then I would be in some other natural science like biology or something. So this is a little bit the background on me giving this talk. So what I think that we should do today, we should talk a lot actually about textures. And textures is something that we in geology use when we describe how these different minerals occur together in the bedrock. So we will talk about minerals versus rock types. What's the difference between those two concepts? We'll talk about ore. What's an ore body? What's it made of? And we will talk about different ore types and how they are formed in the crust. We will go through the mine basically, and I will try to explain the different steps that the mining companies are doing in the mine to extract the metals. Then we will do a comparison between 2 different ore deposits, similar ore deposits, but mineralogically different. So we will have a look at that. And in that sense, we will talk about what is called penalty elements and also byproducts of this mine. And we will finish off with saying a few words on mine waste, basically the 2 types of mine waste and what the environmental concerns would be from those. So textures is sort of the backbone of the whole talk here today. But we will start big. We will start with rock types. This is a map of Sweden. It's a geological map of Sweden where all the different colors show the different rock types that the Swedish bedrock are made of. So you can plainly see that it's very heterogeneous. And this is looking in the 2 dimensions, in the 2D. So if we look to the right, we will have a 2D map, and we will see that towards the third dimension, towards depth, the crust will be equally heterogeneous. So it's a very heterogeneous bedrock that we're typically working on. And all these then different colors would be different rock types or different units or parts of the bedrock here. And then in geology, we have all sorts of weird names for these. I'm just moving my window a bit. So all sorts of weird names for these different rock types. And here I've only mentioned just a few, and a few of the more common ones. And you've all heard about the granite. That's a typical rock type in Sweden and throughout the world. Perhaps you've heard of a volcanic rock called basalt. It occurs mostly most part of Iceland is basaltic in nature. Then we have a different rock type called a schist. This is a rock type that has been deformed and metamorphosed. It has changed its character through deformation. And the black dots here, or dots, the little specks here, are garnets, and they are sort of blackish. If they were more reddish or transparent, they would be gemstone quality, but this is a schist rock here. And then we have another rock which is with a weird name called gabbro, for instance. And then we have two sedimentary rocks at the bottom, which is limestone and sandstone, then formed at the ocean floor, or on the ocean floor. So the difference then between a rock type and a mineral is that we will use the granite here as an example. The granite would be the rock type. So if we take a granite sample and we put that under the microscope, the sort of background picture here will be what we see. We will see a bunch of different minerals that relate to each other. They sit in various orders in this one. And they will also have sort of weird names. Typical here would be a plagioclase or biotite. You may have heard about quartz. It's a fairly common mineral, but all sorts of weird, namely minerals in this one. And we will see then these different minerals will be resembling the individual bricks in this. This is a brick wall up to the right here. The individual bricks would be the minerals, and the minerals or bricks together would be the rock type, the brick wall, so to speak. So that's the relationship between minerals and rock types then. Then if we look more in detail on the different minerals, then they are made up of different elements, and they will have a crystal structure to them when they grow. And we can use then plagioclase, for example, and to form the plagioclase mineral, we will need sodium, calcium, aluminium, silicon, and oxygen. And it will grow according to a certain crystal structure, and then we would call it a plagioclase in geology. So we will have the elements forming the minerals, forming the rock types, basically. Then the concept of ore is a completely economic term, which essentially means that there is concentration of metal, any metal basically, where a company can make a profit from mining this, from extracting this from the crust. There is a high enough concentration so they can make a profit, then it's an ore. If they can't make a profit from extracting the metal, but the metal is still there, then we would call it a mineralization instead. So and this goes for any metal basically in the crust, but we can say that we use the element gold here. So all these green apples will be gold atoms occurring in the crust, and they will be scattered sort of all over the place in very low concentrations, but a little bit all over the place. And then during geological past, then different geological processes will have moved these atoms around, which means that in certain places in the crust, there will be a higher concentration of gold. And if the concentration is high enough so that the company can make a profit from it, then it's an ore. If they can't make a profit, it's not an ore. Then they would not be interested in it. So this is the concept of ore, and it follows very much the commodity, or entirely, essentially the commodity prices, the price, the amount of money that we are willing to pay for gold or pay for iron or copper or so on, which means that there is also a variation in the concentration in an ore body. It's not just a copper lump in the bedrock. We will see that there are parts of the ore which are richer and parts which are poorer in copper, for instance. So at a given commodity price or metal price for copper, everything within this red area will be the ore. That is the part which is of interest for the company. If we then increase the metal prices a bit, then the lower grade parts of the crust here will be of interest because it will be economic to mine now this volume. So this follows the commodity prices. So the volume of an ore goes sort of up and down together with the commodity prices, which makes it sort of a living concept, ore. Then we have three different ore types according to metal. This is basically how the industry a little bit divides these different ore types. We would do it differently in ore geology, and I will come to that. But the three types that we have is iron ores. We will have base metals, which is copper, zinc, and lead. And in those, we will also have a bit of gold and silver, typically. And then we have precious metals, which is gold and silver. So those three types. And to the right, I have just listed a bunch of sort of weird names, weird minerals that are the main ore minerals in these different ore types. So for iron, they would mine magnetite and hematite, for instance, which are iron oxides. For base metals, they would mine chalcopyrite, which is the copper ore mineral, sphalerite for zinc, and galena for lead. Precious metals will occur typically as electrum, which is a gold-silver alloy in the crust here. So gold and silver is very tightly intergrown together in these deposits. But this is according to metal. If we then have the view of an ore geological scientist or researcher, then we would classify them according to genesis, the way they are formed instead, the processes that are responsible for forming these different deposits. Then we group them differently than the industry does. So for an ore deposit to form, we need a bunch of different geological processes that act together, not necessarily at the same time, but in the same place over time. And over time, I would say something that happens instantaneously in geology would be considered perhaps 10,000 years, all the way up to maybe 1 million years for an ore deposit to form. But we need then the ore deposit will be the footprint of all these different processes that have acted together. And this footprint is dependent on each and every one of these different processes. So the processes here, I put in like A, B, C, D, and so on. So if one or two of these processes would be missing, would not be happening in this place, then we would not form an ore deposit. Then we would have perhaps a little bit higher concentration of metal, but not very much. So it's dependent on these processes to act together. So what we're doing in ore geology research basically is to try to understand what happened 2 billion years ago, 10 kilometers down in the crust. 1.8 to 2 billion years ago, a lot of the ore deposits in Sweden were formed. So we are sitting sort of here today and trying to figure out how those were formed, sort of way down in the bedrock at that point of time, which obviously then is super difficult, but this is the fun part of it. This is what we're aiming for, to understand these processes. So I will talk, I will describe two different ore types that are common, occur in Sweden and elsewhere as well. One is called the porphyry copper, where copper is the main commodity, but we will also have gold typically and a little bit of molybdenum in this deposit, but copper is the main commodity. And then in the animated picture here, which is sort of coming to a halt now, is where you've seen the plate tectonics. These continents, they move around over the globe here. They will drift apart, they will collide with each other over geologic time. And all these processes, these movements, generate these processes that we are dependent on then to form the ore deposits. It's mainly in the boundaries between these different plates then, or continents as we see them here, but plates, where the interesting stuff is happening. So in the bottom left, is a geological environment that we would call a subduction zone. This is a place on Earth where the oceanic crust collides with the continental crust. And as the oceanic crust is more dense, it's heavier, it will sink underneath the continental crust. And eventually it will come down, it will be warmer and warmer, and it will melt. And this molten material will then, through density contrast, will migrate through the continental crust upwards. And if it reaches the surface, we will have a volcanic eruption from this. And many times they stay cool and stay a few kilometers down. They never reach the surface, basically. And this is what we call an intrusive rock, because it intrudes the continental crust here. And this is the way, for instance, granites that we talked about earlier, how they are formed here. And in some of these intrusive rocks, we will have an enrichment in copper, for instance. So the bottom right picture is a picture from an ore. This is a porphyry copper, would be the Aitik deposit in Sweden, for instance. And this is a picture of an Aitik sample where the yellowish minerals or small grains that we see here are the ore minerals that the company is after. But it's not very much. It's sort of scattered a little bit all over, but that's a typical texture then for porphyry copper. So, and this was then a Swedish example. There are many examples worldwide. And Chile, for instance, is one of the nations that have a lot of these really big porphyry copper deposits. Another ore type is what we would call a volcanic massive sulfide, or VMS deposit. And they are formed in an environment like this. This is just an artist sketch of a section of the crust, where we can see that the crack in the crust here is what we would call a mid-ocean ridge. And a mid-ocean ridge is something that we see here. This is the Mid-Atlantic ridge. And it's an extremely long mountain chain, which is rather high, actually. It's from the ocean floor to the top of this mountain chain, or top of this ridge, is over 3,000 meters. But it only sort of sticks above sea level in just a few places. Iceland would be the big place for this, and then there are a few islands. So this is one of the world's longest mountain chains, but we never really see it. But this is the chain where we have a spreading zone, where we have a formation of oceanic crust newly formed here. So this is the mountain range. So in this area, the processes that are important are that we have ocean water then percolating down into the fractures in the crust. And as the crust is rather thin, the water will heat and it will come to a boil. And when it boils, it will migrate upwards again. And during the boiling, it will leach metals from the oceanic crust with it. So at the site of the larger red arrow here is where we would find something like this. And this is what we would call a black smoker formation. So this is water, basically, very warm water, about 350 degrees centigrade, coming out from these vents on the ocean floor. And the smoke, as we can see them, is that because they are then packed with metallic particles. And these metallic particles will settle around these vents and form small mounds. And then later on, when these small mounds, or metallic hills, so to speak, have been integrated in the oceanic crust from sedimentation above, then they would form what we would call a VMS deposit, or a volcanic massive sulfide. And the massive part of it is because they look something like this. They are sort of metallic all the way through, very rich deposits here. And sulfide then is a group of minerals, which means that you have a metal connected to sulfur, basically, as a mineral then. So then 2 billion years ago, this ore deposit, we can use the Skellefteå district because this is one of the places in the world and in Sweden where we have these deposits. There are over 80 known VMS deposits in the Skellefteå district. And in 1924, they found one of the larger ones, or richer ones, which was then formed close to 2 billion years ago. So this is one slide basically on finding the ore or exploration. This could be an entire university course in its own, but I will leave it at this one slide. Finding this ore through different methods or tools then, and with the aim that the company has then on mining this ore. And then it all comes back to the textures. Textures is key, so it sort of sets the framework for how efficient this mine can be when going through all these different steps. So a mine, they would drill and blast the rocks, then they would sort the rocks, they would sort it in two piles, so to speak. One will be the ore, the other one will be the waste rock, the stuff that they don't want, basically. So they take the waste rock and they put it on a stockpile next to the mine. Then they take the ore to the crusher, and then they crush this ore. Then it's all a matter of reducing the particle size. So they crush the ore in one or perhaps two steps, and then to take it to a mill to reduce the size even further, milling it maybe 1 or 2 times here, so that the final particle is maybe 100 micrometer large. Then they take it to the mineral separation phase, where they want to separate the mineral of interest, the ore mineral, for instance, copper ore mineral, and everything else, which is then considered waste minerals. And the waste minerals here would be called tailings. And these tailings are what is then being stored in the tailing ponds around these mines here. And then from the separation part, they will have a mineral concentrate, a copper mineral concentrate. That's the product of the mine. So this is the operation that is done in the mine, and then they take the mineral concentrate and they ship this to the copper smelter where they melt it and extract almost pure, not really, but almost pure copper as the smelter product then. And then they can use the copper for making all sorts of things that we all need. So these are the steps in the mine, mining the ore. Then typically in media, I would say, different ore deposits are compared, and they are done this with using numbers, and it's not always, I would say that it's rarely done geologically sound. So just for an exercise, we will go through to compare 2 of these deposits, and these are sort of fictional deposits. We will discuss ore A and B, and we will talk about grade and tonnage. And for the first ore, then the grade is simply the concentration. Grade and tonnage is something, these are terms that the mining industry uses all the time. Grade is the concentration of the metal that they're after. If it's copper, they have, for instance, a concentration of 0.2%. And then the tonnage, which is the volume of the ore body, how large the ore body is 1,200 million tons. So it's a fairly large deposit, but a little bit low grade considered here. Then the other deposit would be 5% copper, but 6 million tons. It's a much smaller deposit, but richer. So what we would typically see in the media here is when comparing these two, they will compare 0.2 to 5.0 and saying that the 5% copper, that's the better deposit. This is richer. This is the better one that we need or we should go for or whatever. But the 5.0 is sort of considered the better one. But this is geologically not always the case. So I will just sort of make it more difficult by showing what's behind these numbers, basically, 0.2 and 5.0. So this is built on, in the mine, they will drill. They will do what is called diamond drilling. And this is to extract diamond drill cores. These are 5 centimeter wide rock drill cores that they can extract. And these drill cores can be several hundred meters or 1,000 meters long. And then they take these drill cores and they cut them in half. They send one of the half, they save one half, ship the next one to the lab, basically, where they crush and analyze and get sort of the chemical composition of this sample then, of this ore body. So this is the kind of data that they generate. They will get chemical data. And then the company looks at, because they're interested in copper, they will look at these numbers and say that, yeah, well, this looks fine, no problem, very good. But they will also see in their data set that they have antimony, for instance. And then they know that antimony is a problem for them in the smelter. It will be difficult to separate the antimony from the copper. And if it's high in antimony, the quality of the mining product, the concentrate then, will be lower, which means that when the mining company sells their product to the smelter, they will get paid less if it's more antimony in the mine here. So this is a problem for them. So now they need to figure out where is the antimony compared to the copper. And this is textures. Again, we come back to this. So we will look at an ore particle. These are ore minerals. And these are a bunch of weird names. The yellow thing here, which is the chalcopyrite, that's what the company is interested in. Then we have some other stuff, which is called pentlandite, pyrrhotite, pyrite, and magnetite, and so on. Doesn't really matter. We will look at the chalcopyrite in this case. And what the company wants to do then during the crushing and milling is that they want to liberate the copper mineral, the chalcopyrite in this sense. So they need to know how large are the copper minerals, the grain size of the copper minerals. So then they want to crush their ore down to that size so that each particle is the same size as the chalcopyrite, because then it's statistically a good chance that they have liberated the chalcopyrite from everything else here. So this is the main concern. So then we just sort of play with the idea that the blue stuff here will be the antimony mineral. And if it's the same size as the copper mineral, then that's a good thing for the company. This means that they will probably be able to separate those two, and antimony will not be a problem in the smelter. However, this is obviously not always the case that nature throws at us. This could be the case that we have antimony minerals, fine grain, very small, but in this sort of blackish background, which is the waste minerals then. They want the chalcopyrite, the yellow mineral here, not the black ones here. So they will be able to separate the ore minerals from the waste minerals. So if antimony sits like this, then that will not be a problem. That's a good thing for the company.